Okay, so we follow our normal methods. Our normal methods start with step 1, choose our coordinates. And although this bead is in fact traveling in 2 dimensions, we only need one coordinate to describe where it is because we know exactly where it is around that axis just by the time, and so we only need the radius q. And we can work out what the actual velocity of this thing is in terms of q very easily by putting our coordinates in our diagram and converting. Our x is just going to be q cos omega t, and our y sine. In fact, of course, we can pick our zero of time any way we like, and so we could even swap cos and sine almost, but that will do for now. And we know we need to know the velocity, so we might as well work that out now. And this time we have a product rule, because that depends on time, and obviously this depends on time. We move on by calculating the Lagrangian. Lagrangian is, remember, just the kinetic energy minus the potential energy, and we can calculate it. We need to calculate it in terms of q and q dot, but we'll start by calculating it in anything we know, which is x dot squared and y dot squared, which is precisely, of course, why we work this out. And then we have our gravity, and we have our spring. It's very easy to miss this minus sign when you have multiple potential terms, so be careful about that. Okay, and now we simply substitute in. And of course, this term cancels with that term, and we do have cos squared plus sine squared and sine squared plus cos squared, so we can simplify. And this is an excellent time to look for dimensions. We've got half mv squared, that's an energy. That's also a v squared, so that's good. This is mgz, that's definitely an energy, and that's a spring energy. So we have units of energy all the way across, which is excellent. We found our Lagrangian. We then get our Euler-Lagrange equation. We only have one variable, so we only have one equation. And again, substituting in, we only have one term with q dot, but we have several terms with q. Because we've got multiple terms and this minus sign and that minus sign are going to interact, I'm going to very deliberately make it easy on myself by using lots of brackets rather than trying to keep all that in my head. And that's our equation of motion. Let's do some checks. So if we turn off the rotation, then we lose those terms, and we've got what looks just like a mass on a spring. So that's good. If we turn off the spring by turning off K and make this very, very small, the rotation very small, we can pick our phase, and it looks just like something falling under gravity. And if we turn off both gravity and the spring, then we have that just spinning that thing round is going to cause the bead to fly out, which is exactly also what we'd expect.